In this video, we're going to be talking about how to find the attenuation constant alpha, given the open and short circuit impedances, and also given the characteristic impedance Z0 of the transmission line, which we found in the part 1 of this video. So make sure to check that out if you want. Anyway, we had two equations from last time that can help to arrive to alpha. Those were the short circuit impedance was equal to Z0 hyperbolic tangent of alpha, 20 alpha, sorry. This was the first one, and the second one was the open circuit impedance, that is equal to Z0 divided by hyperbolic tangent of 20 gamma. Why will they help us? Well, because they have gamma inside them, and gamma, as you know, is equal to alpha plus j beta. Let's use the first equation to arrive to our solution. An identity that will help us solve this is that the hyperbolic tangent of x is equal to e to the x minus e to the minus x divided by e to the x plus e to the minus x. So if we apply this to the first equation, we will get z short circuit equals to, we rewrite z0 multiplied by the hyperbolic tangent of 20 gamma, which is e to the 20 gamma, since here x is equal to 20 gamma, minus e to the minus 20 gamma divided by the rest, applied in the same way. Okay, so now we multiply both sides by the denominator, so that way it will disappear. Okay, so we write minus 20 gamma. So now on the left side we have the short circuit impedance multiplied by the denominator, so we're gonna just do that directly right here. On the right side, these two cancel out, so we just have the denominator left. So we have Z0 multiplied by the denominator, Z0 e to the minus 20 gamma. Now we can multiply by e to the 20 gamma, so our equation simplifies even further. So we write it right here. So this first term will become e to the 40 gamma plus the second term, this part right here will disappear, so we will have just multiplied by 1, and we won't write it because it's unnecessary. And on the right side we also have this will become e to the 40 gamma minus also this part right here will just become 1, so we have minus z0. Now let's take the terms with exponents from one side and the rest to the other side. So this term we just rewrite it, and the term with z0 we move it from the left, and we do the same thing for the right side. We move this term to the right and we just rewrite z0. Now we can take e to the 40 gamma out in front of the parentheses, so that is e to the 40 gamma multiplied by these two terms equals to the right side, simply rewritten. Now our end goal is to arrive to alpha, which is hidden right inside here in gamma. So now we will just isolate e to the 40 gamma, and that will be e to the 40 gamma equals to minus z0 divided by short circuit impedance minus z0. Now we can multiply the top and the bottom part by minus 1, so we make this fraction look a little bit prettier and easier for us to work with. So we just change signs on both sides of the fraction. Okay. Now, if we were dealing with real numbers, we would have just applied the natural logarithm from both sides and would have gotten the result for 40 gamma. But now we deal with complex number, so it's a little bit different. When we have the natural logarithm of a complex number, z we'll call it, and this z is equal to x plus jy, or ey is the same thing, it's just a matter of convention. And this is in one form, but we can also write it in the polar form, which is re multiplied to the I theta. Okay, so this is the modulus in the phase, and by the property of logarithms we can just rewrite this as the natural logarithm of r plus the natural logarithm of I theta. Sorry, e to the I theta, I rewrote it bad, and this is just equal to the natural logarithm of r plus I theta, and we have plus j to k pi because we are with complex number. So every circle, once we do a whole circle, this repeats. So now if you put this fraction right here in the calculator, you would have something that is equal to 4.139 to the ej to this number right here. So this is our r right here, and this is our theta. I'll just write j everywhere so you don't get confused because it's the same thing. So now we apply the natural logarithm to both sides, okay? And we have the natural logarithm of the left side equals the natural logarithm of our r, which is this right here, plus j multiplied by our angle, which is this right here, plus j multiplied by 2k pi. And now this right here will be just 40 gamma plus j 2k pi for the same reason that we took this term right here. This will be equal to, we just rewrite the right side. We don't need to change anything. It's already done. Okay. So you can see that these two terms just cancel out. And we will have 40 gamma is the result of this is 1.4205 when you write it in the calculator plus j 22024. So now you can see that on the right side we have it very good divided in the real part and in the imaginary part of the number. So now we say that gamma is equal to this part right here divided by 40, and we get 0.0355 plus this part right here, okay? But what is gamma equal to? Gamma is also equal to alpha plus j beta equals to this. So now how do you solve an equation with complex numbers? You put that the real part of the left side is equal to the real part to the right side. The same for the imaginary part of the left side needs to be equal to the imaginary part of the right side. But since now we are interested in alpha, which is the real part, we will say that alpha is equal to the real part of the right side, which is 0.0355, and the unit is Nepper divided by meters. So we arrived to our solution finally. Thanks for watching this video. I hope you enjoyed it, and see you in the next one.